Hello there. Hello again. Welcome back. This is Al. And this here is a special sort of by request tutorial, hopefully a short one, on the topic of smart pointers, which I make a lot of use of. So this will be 94 on smart pointers. First, let me motivate the reason why one might want something called a smart pointer. Suppose you had a class or struct, doesn't matter. And inside your class, maybe you have some data, int, some info, maybe a string. Okay. Now I could have an empty constructor. Let me set this to 0. Maybe I'll have one that takes a string. I'm not using any Unicode here. And let's say M string mster my string. Okay. So there are a couple constructors. Maybe I'll have a function set string LPC's constant use. Whoops. Something like that. Set info. Okay, perfectly fine class. Oh, and maybe want to get the stuff back out. Okay, now I'm going to just create one of those objects. What do you see? No constructor? No. We'll put hello world in. This is a hello world program. Put S object dot get string. That should print hello world. Whoops. Screw it up. Okay, that's a complicated way to go about it. Also, you'll note that we don't have any memory leaks or anything. I could also, if I wanted, make a function foo, which takes a my class MC, give it a different name, and does the same thing, almost. Remember, it can't be it has to be an actual string for that %s. Get info. Sets an info. $25. Well, we can do that. And then call foo. Now that should print out hello world. Then this these equal signs, and then hello world again, comma 25, and another character term, which it did. Any problems with memory leaks or anything? No problem. Now, now the reason why that works is because everything in this class is copyable. Okay? You'll notice that this class doesn't even have a destructor defined. But what if I had a class that, well, in addition to what I've got here, I had like a great big image data in it. And have a given size. Okay. Then make sure to initialize these right. If I don't do anything, this should be no and 0. Well, I'll get rid of that one. Set string is good enough. One constructor is easier to deal with. There. So now we're still where we were. Just added 2 more bits of data, no memory leaks or anything. But now suppose I want to add a great big image to this thing. So first I'm going to say allocate. I'm going to tell it to allocate enough memory to hold the image I want. So that has to be true, and we want to set this image size to be view size. Okay, here I'll put it on 2 lines. That looks maybe a bit better. Okay, now the question is, okay, well that's one part. The question is, what do we do about, when are we going to free this data? We got this data in here. The string frees itself when it goes out of scope in its destructor. So we could do that, right? We could say, and you know, if you've watched any of this is wrong. And you should know why. First, I'm going to tell my object to allocate, let's see, 150,000 bytes. And maybe we want to fill it up with something. So we need access to that data. Non-constant access. Although returning this doesn't change any of the members here, I wouldn't put a const here because we're changing the data pointed to by this thing. If we want to do that this way, which I do because I'm lazy. And how about size? This is const. Okay. Now I'm going to fill this up with junk. So let's last time I did this, I got a divide by 0. Rand %rand. Did you know that 0 is a possible random number? But I think adding 1 is okay. Oh no. Yeah. I don't think I can ever, yeah, that should be fine. And these are bytes. So now that should fill up all the data with some random junk. And we can print out part of it. We have this debug chunk. Let's say we'll print out 120 bytes worth of it. Dump width is 16. Now I'm going to call foo, my object here, which will do what it did before, and also maybe do this too. Maybe print out a little bit more. Okay. Now, do you see the problem yet? It's amazing that the compiler doesn't warn about these things. Object. It's not object, it's called MC. First, let's run up to this point. Okay, here's our object. Here's our data. 150,000 bytes worth of CDs, which I'm going to fill up. Okay. It might seem like a lot, but it's, whatever, who cares? Now, I got the string, hello world, and that. And I print out F10, 120 bytes worth of the junk, which is correct, that's funky. Now I go to foo here. Okay, print out hello world 25, no problem. Print out a little bit more of the thing. All looks great. Come back and look. Look what's happened to my to my data. It all got destroyed. Well, the reason is clear. You see, before we had an object where everything could be copied, and everything had a way of copying itself and keeping track of its data. But these things don't have such a mechanism of keeping track of themselves. Now, we could make a copy constructor that would copy all of the image data into the new MC here, and then we wouldn't lose anything, just like TS string does. But remember, that's 150,000 bytes, or it could be a typical image is more like 1 million. So 1.5 million bytes. We don't really want to copy 1.5 million bytes over to here. I'm going to show you that this runs. It's like it sees this. Okay, it made it. Okay, here's our object. Here's our image data at 13 something or other. FE80E7. Working great. Call foo, and it's gone. Not only that, it's turned to question marks. This area of memory is no longer even valid. It had to go to heap, allocate a new heap just for that, just for our data. Okay. So obviously that's no good. What we would like instead, well, first we can fix the problem one way. Usually This is what people do. Instead of passing the object by value, pass it by reference. What do I know? Oh, const. Okay. And non-const data. And I want a const version. Of data. You see the difference, right? This one I can modify the data, so I can't honestly put a const here, but I can for this. You're not allowed to touch this data. Okay, now in this case I won't lose anything. What I'll do, we'll run up to here. I know what sped it up last time. Hang on. When the recorder is on, it's a bit slow. Okay. Oh. Here's our fictitious image data. Call foo and it's safe, right? And the reason is obviously because we didn't make a copy of our object, so therefore there was nothing to destroy. What happened before was my class, all the members were dutifully copied, passed into foo, and then that copy got destroyed, and so the destructor was called, and the data was freed. But we didn't want that to happen because we only want one copy of this data. There's so much data, we don't want to, copy it like a string. But what we want is to somehow keep track of how many of the use of this class, right? Let me put it that way. That is. Well, this is okay, right? As long as we could disallow copying completely. That's one solution. We could say it's the copy constructor that's messing us up. Just do that, and that won't allow us to make copies. See, cannot access private member. It wants to do this copy construction, but it's not allowed. But that's sort of a solution, but it's not a good solution. And the reason why it's not a good solution is, suppose I wanted to make a list of something like a list of my class objects. Well, I can't really. I mean, they would have to be copied. But what I would have to do is make a list of maybe pointers to them. So that's okay, we could do that. List of Pmon class, PMC. Okay, fair enough. And foo here can take references. our pointers, and everything is fine as long as we don't stick to pointers and references. So I could do this, and I could do this, and so on, and everything's fine. No copies. Oh, no. Oh. I think that's what it is. Yeah. So I can go ahead and I can add lots of these objects to this list here. Now, is that we tend to want to have classes of things that contain lists. And suppose I want to add to the list. Right? Well, let's put foo down here. Suppose foo takes A. Okay. I need something called add. We can take A. And let's see now. Now we gotta be able to get them back out again, right? Int PTR. Well, be very careful. We can only use 0 for the moment. Oh yeah, now to say A get 0. No, what have I done wrong? Whoops. Now what have I done wrong? Get 0. Always. Now the point. And we're still going to be okay. Let me make this smaller so it overrides. Seconds. Should be fine. Should run. And there won't be any memory leaks either. And our data doesn't get destroyed. See, it hasn't turned to question marks. Now, the problem with this approach though, is this object thing. You see, we have to hang on to this object for the entire duration of this function, because if for some reason it dies, then this will be invalid. The A object, where we added here. Suppose I did it like this. I declare A up here. Okay. Now add an object to A. And when I leave this scope, that object is going to die, and A here is going to have an invalid object in it. If I run up to this point, okay, at 10, here's A, here's this list of objects, here's the data, no problem, right? But now, see what's happened? I let go of this object, and that destroyed A's data. So now foo prints out junk. What we want really is some way to let the object know, this object, that we're not done with it yet, even though this is going to die. Somebody else is still referring to it. So what we want is a kind of counter. They call it a reference counter for the data contained in A. So what we want is for this whole class to have a kind of count associated with it, called a reference count. So the typical way to do it, it uses too much time, but the typical way to do it is to start like this. Well, I've got them written down here so I can speed things up. First, now it seems like we're diverting here, but this part has to be done first. This here is a class. Notice the virtual destructor, very important, whose sole job is to increment or decrement a number along, it turns out, and when that number becomes 0, to delete itself. Okay, now the reason why this part's important is because we're going to have our thing derived from this, so when the delete gets called, our destructor will get called as well, because it'll be virtual. Now This part is not needed. That's mostly for debugging, so I'll just get rid of it. So now, what is this interlocked increment and interlocked decrement? All that does is makes the plus-plussing or minus-minusing of this value thread safe. Okay, that doesn't mean that the class is thread safe or that anything that we do after this is thread safe. It just means that this won't crash if it happens to happen in two threads at once. But really, everything should be protected in a different way. Okay, so first I'm going to derive from this privately. And the reason for that is we're going to need two more classes, one of whose job, this one, you can't see it yet, is to manage calling these two functions, and only this class shall have the right to do this. Okay, so by making this derivation private, nobody has any access to these functions from the outside. Okay. Next, this refPTR, reference pointer, which I have written down here. Now, the reason I don't have this in a funny color is because you never see this one. This second stage part is never visible. You'll never see it, so there's no need for special color. Now, a refPTR is an object, as I said, whose sole job is to call this function or this function on an object that's a refs, which is what our object is. Okay? When it is constructed, it increments this lrefs by calling that. When it's constructed with a refs. When it's constructed with something of its own kind, it copies the object part and increments the reference count. Assignment is slightly different. If we already have an object, we have to release one reference count from that. Then we reassign, do just like this here, assign our object to this guy's object and increment the reference count. When we die, we decrement the reference count. Okay, now how does this come into play? This comes into play in the final step. This is the smart pointer step. Now this is the template class, which is where it all comes together. Because now we can use any object of any type. SMARTPTR, or smart pointer, derives from refPointer. Okay, it has an empty constructor. Otherwise, it takes a T star, whatever we put in here, and constructs the refPointer bit of itself from that. Now remember, refPointer takes a refs object in its constructor. So therefore, whatever this T is, it has to be a refs, which our thing is. But we did that on purpose. Now, in order to allow all of this to work, because so far nobody has any access to this revs, is that we have to make this thing our friend. So I'm just going to write it down. Now this is the class that is going to be constructed from our class and contain and manage the reference counting. If it's our friend, then that will allow it access to ref pointers, refs, and all this increment and decrement stuff. Okay, now what else about this? There's an operator arrow which returns a pointer to whatever the type is, and so that's how we access the member functions and data of T. There's a star thing which I never use. There's this which I never use. There's this which I use occasionally, and this more for debugging. Don't need it. Is null is mostly useful. Now, in fact, what I'd like to do is make this a type def. I'll do it down here. Usually for since smart pointers are like pointers, I could say p my class, but instead of using p, I use a letter small h for handle. Okay. So now I could have done that up here, but it works out the same. Alright, now I'm not going to touch this yet. First off, I'm going to change A here to take handles to my class. Change all the P's to H's. Okay. And that part I think I can leave the same. Okay. So now I could say this, but I don't want to say that. I want a handle to my class H. I'm going to call it H object. New my class. That should be the only time I ever allocate any my class object. Okay, so these are all H object, and now they act like pointers. See? It's just as if the whole thing became a pointer. Now A here just takes again a handle, and what you're going to see here is by adding this object to A's list, its reference count will go up. And so when we leave the scope here and the reference count goes down again, it won't go to 0. So there'll still be a reference count on this object, and A won't destroy itself, and foo will have a valid object. Now, ambiguous symbol. Gosh darn it. How is that getting in there? Let's see. Use different letters. Maybe fast. Faster. Just do that. I think we should be okay. We need all that craziness, if not to find lit. Maybe. Okay, work. Alright, now time. Well, this is really long, but it's actually pretty much at the end. So if we can just follow through these, what's going on here. Now here's H object. Okay, it's a ref pointer, it's all junk at the moment. I construct a my class and assign it to that. Now the object has one reference count, and it is a my class. It has a my class in it. Okay. Now I'm going to set those. When I use the arrow operator, that takes me to here, and it casts the contained object to my type, my class, calls that string, and that works. See, there's the string. Same for the others. Allocate, go to here, and here's my data. Hello world. Some of the data, 1, 3, 4, 9, blah, blah, blah. Now, here's the crucial bit here. Currently, the reference count is 1. Okay, now I'm going to add this object to this A thing, which has a list of smart pointers to my class. F8. Already you can see the reference count has gone up to 2. And now it's being added to the list. Okay. Well, it's currently 2. But it should be 3 for a minute anyway. Now it's 3 because we got 1 reference count in the list, 1 reference count passed in through the copy constructor that incremented the reference count, and now it's been added, and then the copy will be destroyed and that will go down to 2 again. So it's 2. Now we're going to leave the scope. And we can't see it anymore because H object is dead. But notice that the memory hasn't died. And if we look at the head node of A's list, here's our object, still surviving with 1 reference count. So now I can call foo here, which has made now a copy of this list and bump the reference count up to 2. And I can still print things out. Hello world 25. Still print out the data. And when I go back, the reference count is now 1. And when this A dies, its list will be destroyed. Well, it didn't show it, but here you can see it. The memory was freed. So that's smart pointers in a nutshell. And next time I'll show you the one. Well, there's one slight addition to this, and that is, what if I wanted to do this? Can't do it, right? Because byte is not a refs. But there's a way around that, and you can make smart pointers to any object for the special magic trick that I have. But not worth going over. Okay. Well, I hope that helped. See you.